Hello, everyone. Let's keep going. The last time we were together, we had talked about Chapter 19 from the Katz book, Calculus-Based Physics. It was on other, slightly different topics. Still thermodynamics, but it was on temperature, thermal expansion, and gas laws. Temperature, thermal expansion, and gas laws. That was Chapter 19 from the Katz book. Let's stay with the Katz book, Calc Treatment. Chapter 20, there's some problems we're going to do from there to our best of our ability here. Let's see what we can do. 15, 17, 21, 55, 56, 58, 59, 61, 62. Again, we're in thermodynamics, just a little different aspect of it. We're still talking about thermodynamics. Okay. And see what we got here. So still talking about thermodynamics a bit, guys. And we'll kind of take it from there. Let's just start it from the beginning here. Let's go problem number 15. Problem number 15, and again, this is kinetic theory of gases, that aspect of thermodynamics. Problem number 15, the mass of a single hydrogen molecule is approximately 3.32 times 10 to the negative 27 kilograms. There are 5.64 times 10 to the 23 hydrogen molecules in a box with square walls of area 49.0 square centimeters. If the RMS speed, root mean square speed of the molecules, is 2.72 times 10 to the 3 meters per second, calculate the pressure exerted by the gas. When they're saying that there are 5.64 times 10 to the 23rd hydrogen molecules in a box, now this is kind of interesting how that all plays out. The mass of a single hydrogen molecule is approximately 3.32 times 10 to the negative 27 kilograms. The hydrogen molecule tends to be diatomic. So they're probably looking at the whole definition here, the molecule being a diatomic gas. Let's take a look at it here. Let's see exactly how there's various assumptions that are being made. They're saying there's 5.64 times 10 to the 23rd hydrogen molecules in a box with square walls of area 49 centimeters squared. What does that mean? Well, there are 6 walls to that square box. Each wall is 49.0 square centimeters in area. Each wall is 49 square centimeters area. That means 7 times 7 is the 49. It's a square, remember, and it is a cube. All the sides are equal length. 7 centimeters on an edge, every single edge that there is there, is the way you want to look at it. That's the case. Let's see what they're trying to say here. Well, like I said, we can say a lot, and we'll try, and indeed we'll try to say a lot. Okay. For problem number 15, The VRMS, the RMS speed, VRMS, root mean square speed, means basically the average of all the squares, square rooted, which is equal to, with all the mathematics that we have done earlier, we're dealing with absolute temperatures here again, guys. We're here. We got that. So I guess if you take this whole quantity, square it, and take this whole quantity and square it, that's the same as squaring this whole quantity. Basically, you take this square-rooted quantity and square it, take this square-rooted quantity and square it, and you end up getting the V average squared, which is the VRMS squared, which is the V average squared, is equal to 3 kBT over M. Again, they're not, I mean, we'd have to look up to see exactly. I don't think they're going to put single hydrogen atoms in there, but I mean, let me just kind of, just to check real quick here on the fly, you guys. Yeah, I mean, the proton mass, the mass of a proton, give or take a little bit, is about 1.67. If you double 1.67, if you double 1.67, you get about 3.2. So, I mean, the proton mass is 1.67 times 10 to the negative 27. So, if you were to double 1.6 or 1.67, you'd get about 3.32, 3.33 something, 3.32, 3.33 times 10 to the negative 27. So they are, just for the record, being faithful, I guess, to the chemistry to a large extent. Hydrogen to diatomic gas, there's two hydrogen atoms that are bonded together, H2, and that comes out to the 3.32. Let's see what they had here. Right. For this one, in fact, yeah, it's quite good. I mean, we're saying it's about 1.67 for a proton times 10 to the negative 27, which is about the same mass as a hydrogen atom. And if you double that, the 1.6 something doubled is 3.32 or thereabouts. 3.32 times 10 to the negative 27 kilograms. Okay, so it's a diatomic gas. So we're looking pretty good there. Tell you what, take this guy and multiply it by a half M. Go one half times M, multiply the VRMS squared by 1/2 times M. Multiply this by 1/2 times M. The M's cancel. It's pretty significant. You get to here. If you take, this quantity and multiply it by N, the total number of particles present, multiply by capital N, okay, now it's looking real familiar all over the place. So you got something like that there. Well, do you remember that just this guy right here? Okay, so we got this, we got that. It's equal to all of this. That's all the kinetic energy that's in there. Well, that's the internal energy of the system, in a sense. It's total internal energy of the system that we got. So if that's what we're looking at, what do we mean? Well, let's just take a snapshot of him. Let's do this. We all remember that PV equals nRT. We all remember that PV equals capital N kBT. Well, these guys are equal to each other. That means these guys are equal to each other. N KBT is equal to nRT. True. And they're both equal to PV. Okay, yeah. Okay, now what? Well, do you remember how you want to do this? I mean, there's a number of ways we can do it. I'll tell you what. Why don't we do a number of things here, I guess you could say. There's something I had said there. I didn't necessarily need to say it, but I'll tell you what, let's just say it anyway. Let's come right back here. What do you say you just solve for this guy? You say, okay, this is the NKBT right here. And you've seen the whole speech we delivered on that. Why don't we do this? Why don't you multiply by 2/3 on this side, and why don't you multiply by 2/3 on that side? The 2/3 cancels with the half, and you just got 1/3. You just got capital N over 3 true. And that's equal to PV. We already said that. I mean, we said that back here, that it is, and we got this, which is kind of interesting. I think this does it. I think this is the hardest part of the problem, you guys. If we can get down to here, problem solved real soon. Problem solved real soon. Why don't you divide by V on each side to get the pressure? The pressure is going to equal N over 3 times MV RMS squared, true, divided by V. You had PV. PV here was equal to that. PV was equal to that, but if you divide by V on each side, bam. The PV was equal to this. You had a V right here, it was just equal to that. You divide by V, you're right there. So divide by V, and you have that. Well, that tells us a lot. When you're here, guys, as far as I'm concerned, it's all worthy of emphasis, I guess you could say. If it's looking like that, what do you want to say? Just say what we normally say again. Let's solve it. Let's see what they want the pressure. If they want the pressure, they gave us that N was 5.64 times 10 to the 23. That's N. The M, and this is a they're faithful to the real life chemistry that it is a diatomic molecule, and this mass reflects the diatomic nature of the hydrogen molecule. That's M. They told us it was 2.72 times 10 to the third times 2.72 times 10 to the third. That's VRMS squared. Sounds good. The 3's the 3. The volume. They told us that the area under consideration was 49 square centimeters. We have to, I don't know, it's reasonable to think that not talking about all 6 walls added together being 49 square centimeters. It is 49 square centimeters per wall. Okay. What is the length of an edge then? The length of an edge is, well, the side squared gives you the area of the square side, that's 49 square centimeters. Square root of 49 is 7. 7 times 7 will give me the 49. Okay. 7 centimeters. That's 7 times 10 to the negative 2 meters. The notation you used is kind of, up there, but the big thing is you got to cube that. The side cubed, you guys, will give you that. So let me that's all it is. So we play the game here. You go d squared. This is the side. It's length d. D times d times d. Length times width times height is d times d times d is d squared. D times d times d is d cubed, rather. I'm sorry. So that's the pressure. You work this thing out, guys, and you're in pretty good shape. Typically, I'm not holding you accountable for the significant figures. Approximately equal to looking pretty good, guys. So that's number 15 for us. Let's go to 17. Let's see what we can say. Okay, guys. What about 17? The noble gases, neon, atomic mass 20.1797 small u, and krypton, atomic mass 83.798 small u, are accidentally mixed in a vessel that has a temperature of 90 degrees Celsius. What are A, average kinetic energies, B, RMS speeds of neon and krypton molecules in the vessel, and that's it. Okay, since they are both in the same container and at the exact same temperature, or at the same temperature, they have equal energies on average. So there's a lot we can say. Let's just get a few things out of the way for us. We know that kinetic energy average per particle, per atom in this case, kinetic energy average per particle, or per atom in this case, as we said, is 3/2 kBT. That's just for one particle. So, I mean, since they're both in the same container and at the same temperature, they have equal kinetic energies on average, right? If that's the case, you guys, we've got what we got here. What does that come out to? Well, 3 halves is 3 halves. 1.38 1.38 times 10 to the negative 23, 90 degrees Celsius plus 273 degrees Kelvin. 90 plus 273.15. 273 oftentimes gets used. The book is using, in some places, using 273.15, so let's just kind of be aware of that. That right there, all of that, when you take care of that, is giving us this at the end of the day. 7.517 times 10 to the negative 21 joules. Okay, that is the average kinetic energy for each one of them. Now look, they're going at different speeds because one's a lot more massive than the other. But as far as kinetic energies are concerned, on average, they both atoms, both types of atoms have the exact same kinetic energy on average. Doesn't mean they have the same speeds because they don't have the same masses. So that's it. That ends it right there for that one. B, they're trying to, well, how fast is one going? How fast is the other going? Well, the rest is a little bit of, I mean, the basic move you're making for both of these is if you want to find the kinetic energy average, that's 1/2 m VRMS squared. Fine. VRMS squared, multiply this, and you already got, you just figured that out. That was the average kinetic energy per particle. The KE average per particle was that right there. Right here. All of this right here got us to that. So they're pointing to that for the whole, at the end of all that. All right. So you already found this out, so that's good. It's the same for both of them. The mass is going to throw a wrench into it. The more massive object is not going to travel as fast, doesn't need to have the same amount of kinetic energy. The less massive object will be going faster for the kinetic energy to be equal. So let's just solve it for both in a sense, kind of looking at it like this. You got VRMS squared, multiply by 2 on each side, and divide by m. KE average per particle. I don't want to, I don't want to write a book on that thing. You know it's just for one particle now. Divided by m. If it was all the kinetic energy put together, it'd be n times that. Well, then I have to have all the mass that's in there as well for a particular particle. So capital N here, capital N there, they cancel out, you still get the same answer. Kind of interesting. Notice how this has a lot to do, if you multiply it by n, this has a lot to do with the amount of internal energy that's present. So temperature plays a huge role in everything that's going on. Fascinating in its own right, Well, there it is. This is what it's looking like. If you square root both sides, the thing that's going to make it happen just square root both sides. That's what's going to make it happen. That's it. I mean, that's the thing that's going to make all of this happen for us, guys, regarding all of this. So you take a look at it. That's the blueprint. That's the blueprint right there of what we're doing. They're talking about both. Let me just write this a couple ways. I guess you could write it. I mean, let me write over here. VRMS for neon is going to be the 2 KE average we were talking about. You've got this right here. And then the other one's for krypton. It's the same thing. I'm not, look, the KE average was the same for both. They're in the same container. KE average don't matter. Over for this guy, and the other guy is NE right here. I'm sorry about that. All right. It's about where we got to go to make it happen. This is it. This is it. This is what we said. You put it up here. You're going to put in the numbers, and it's going to happen for us. They told us how many atomic units it is. So you got to be a little careful here when we do this now. I want the mass of a single particle, real life mass of a single particle. Well, the numbers are awful. They got different numbers flying up different places, I guess you could say. VRMS for the neon, and here goes. 2 times the KE average. Well, we just said way over there to your far left, times 10 to the negative 21. And, krypton, I'm sorry, forgive me, neon rather. Let's see here, guys, for sure where I'm going. For neon, rather, guys, this is just neon. I'm sorry, forgive me. This was the same for both. You multiply by 2. The atomic mass is this many units of atomic mass. 20.97. Each single unit of atomic mass is roughly the mass of a proton. And there it is. And this is what you're going to grind out, guys, and see what you get for an answer. Now, neon is not as massive as krypton. So it's going to be probably going at a good speed. VRMS .93 meters per second. That's roughly roughly 670. So this is roughly the speed of a neon atom in that environment. This is a perhaps more accurate assessment of that. That's how fast they're going. It's the same exact argument, ladies and gentlemen. It's the same exact argument that will proceed in regard to krypton. Now, krypton's not atomic mass of 20-something. It's atomic mass of 80-something. That's like more than, it's on the order of more than 4 times more massive. It's more than 4 times more massive than the krypton atom. 4 times more massive, that means the square speed is 1/4 as much. The speed should be about half that. If the square speed is about 1/4 of that, because it's 4 times more massive, it's going to be 1/4 of that, the square speed. The regular speed will be the square root of 1/4, which is half, about 300 something. So let's see where that's at, 330, thereabouts. Well, there it is. Let's stay with that guy. And let's go. Here we go again. You've got this. You got the 7.517 times 10 to the negative 21. Now we discovered that a while ago. Way down there, guys. We discovered that. The atomic mass units is not 20-something. It's 83-something. It's a lot, relatively speaking. The atomic mass unit, each atomic mass unit is about the mass of a proton. Or the amount, maybe the mass of a hydrogen atom, mass of a proton, thereabouts. We're not going to worry about the formalities. Something like this will be given to you, or something you can look up to find out what 1 atomic mass unit is. Grind that out. What we got is 328.755 meters per second. It's about half of that. Sure is. I mean, we figured it'd be about half of that. And it is. It's going a lot slower. Substantially slower, but the average kinetic energy of each atom is the same. Okay? What is that average kinetic energy? Well, we said that right here. So we got it right there. Okay? Let's go to 21. All right, guys. We know it's thermodynamics. I'll get rid of this one, give myself a little bit more room. We're doing some of this stuff. "21. In a cubical container with sides 4 centimeters in length, 2.0 times 10 to the 24th helium atoms, each with the mass 6.64 times 10 to the negative 27 kilograms, move each with mass, and they move with RMS speed of 1.50 kilometers per second. What is the magnitude of the average force exerted on a wall by the helium gas in the container?" Okay, pretty straightforward stuff, guys. We are going to keep looking at it, I think, in a relatively straightforward manner when we look at this kind of stuff. Guys, we remember for 21, we always got this on our mind. They tell us it's a good assumption to make in a wide variety of circumstances. That's exactly the same as this. Okay. Yeah, true. Well, we've already kind of been down this road. Let's go down the road again. The average speed, I mean, the average square speed, which is the RMS speed squared. So I could leave it like this. I don't want to confuse you more than I'm going to help you, but this is fine. When you say something like that, it's identical to saying this. The average of the squares. If you get the average of the squares, that's the RMS speed. The VRMS squared is the average of the squares. So one or the other is fine on that. Let's come down this path then. Average of the squares is equal to 3/2 kBT. Yeah, we've said that before. In one way or another, we have said that before. Very recently, in fact. What do you say? You multiply by 2 on each side and divide by m. Multiply by 2 on each side and divide by m. Okay, this is obviously looking very, very familiar. Square root each side. If you square root the average of the squares, you get the root mean square. And that's equal to So there it is. Absolutely. Well, okay, great. See what you want to say. Let's, like for the heck of it, forgive the gymnastics here, but let's do a little more gymnastics. Square the root mean square. That's the average of the squares, which is the same. Well, okay, let's go another path, guys, if you don't mind. If we can let's try this again. I'm going to solve for t. Let me just put it that way. Let me just solve for t. Let's square both sides. And then after I'm done squaring, let me square both sides. And then let me multiply by m over 3BT on each side. Forgive me. I will square both sides, then let me multiply by M over 3KB. Well, this is easier. Let me just see here. This is easier done than said. Let me just not talk too much and just do it. Let me square each side. Let's multiply by M on each side and divide by 3KB on each side. It's MVRMS over 3KB. That's pretty important. I mean, they all stem from the same equation, so we can get there pretty efficiently if we want to do so. If that's the case, what kind of a temperature are we talking about here, guys? At the end of the day, guys, they're saying a lot of stuff here, but they're trying to say, what is the magnitude of the average force exerted on the wall by the helium gas in the container? There's likely a number of ways we can take this thing, but let's go with where I went here. I got the temperature, and for some reason, I just think that's a good way to go with the average force, because somewhere I can put that, somewhere I can come back to these guys, to this guy, and to this guy. Somewhere I can come back to there when I need to, because pressure's already in there. Pressure's in here, pressure's in there, and let's see where that's going to go. So let me get a little more chalk, guys. Let's see what I can say. Basically, at that point, just plug in all the values you got that you know. So let's solve for T, and this might be of use to us down the road. If they ever ask you how to solve for T, we're doing it anyway, even if we don't need it, but we know how to do it if we are asked to solve for T. We are told that the mass of the helium is 6.64 times 10 to the negative 27. That's the mass of each particle. It is going at 1.5 kilometers per second. That's 1,500 meters per second. 3 is 3. 1.38 times 10 to the negative 23rd is what it is. Go. From there, just go with it. What do we got? T is 360 So here we go. Didn't necessarily ask that specifically, but it's good to know how to do it, and it may be useful to us down the road when we actually try to apply it now. Apply what we already know. Here's what I mean. PV equals nRT, PV equals capital N, K sub BT. The pressure divided by V on each side is right there. It's pretty important. I mean, we already know this. We've seen it all over the place. And we know that. So P equals that, huh? That's N, capital N. This is the case of B. Kelvin. They told us each side was 4 centimeters. We got to stay MKS system of units, guys. If each side is 4 centimeters, that's 4 times 10 to the negative 2 meters. And when you cube it, you get the volume. When you cube it, you get the volume. At the end of the day, you guys, this is where it's at. I mean, you do this, and you're getting a pressure . 1.55625 times 10 to the 8th pascals. That's the pressure. So 1.55625 times 10 to the 8th pascals is the pressure associated with this situation. Okay. If that's the case, what's the force? There's a mistake in the answer key. I mean, there may be. I mean, there's in the answer key to which I have access. They made a mistake, to the best of my understanding. Let me problem 21, chapter 20. Yeah, they have the wrong answer. At the end of the day, they're going to give a force, which is not the answer. They're giving 3.74 times 10 to the 5th newtons of force when we calculate force, whereas the answer is going to be about 2.5 times 10 to the 5th. Okay? I'm just looking at this as best I can, guys. I can't see where they would get that mistake. I think what they did is they multiplied by 3/2. I'm not sure. For the life of me, I'm not sure here. They might have. There might be. Yeah, there might be an issue. There's some issue here, but for the life of me, I don't know what that issue would be. These equations are for the basic understanding of what we're doing with the right assumptions allowed to us. With the right assumptions being made that are allowed to us to make, these equations, this equation, and generally, these two equations are the ticket for a lot of things if the assumptions inherent in those equations are allowed to happen. They are allowed to happen for this problem. And so those two equations are what are going to get us there as we do this. In addition to something like this happening here. I'm not sure what happened there. In the answer key, but the answer key is wrong. So you're about to see the right way. I think they might have just made a simple arithmetic error. Their logic, I'm sure is correct. I'm sure their logic is correct. They probably just put the wrong numbers in some place. But to the best of my knowledge, to the best of my understanding, they did make a mistake. So let's finish it out. So the pressure that we're dealing with is this. Now what? It should be pretty straightforward stuff from then on, guys. What happens what happens is this. I mean, pressure is force over area. Force equals pressure times area. Force on a wall, on one of the walls, is the pressure, which is 1.55625 times 10 to the 8. Let's see what we got here. All right, so that's it. I mean, and this is squared. I mean, this is on a wall. So that's just squared. Okay. When we take that and do it, we're not getting the answer they got of the 3.74 times 10 to the 5th newtons. We're getting 2.49. I'm sure their logic is spot on. They probably just plugged in the wrong number. Might have been just a careless mistake there. To the best of my knowledge, this is the way it has to be done. Okay. And that's the end of it. You know, and the comment was made, again, just look at it, follow that logic, and I think you should be okay. All right, guys, let's go to 55, and we'll kind of take it from there. Okay, guys, for 55, all right, guys, let me leave it like that. My luck, this thing will come down and smack me right in the face. I don't think it's in your guys' way, though. Is it in your field of vision? Is it an issue? It looks like it's okay. All right. Let's take a look at 55. A container is filled with a gas at a temperature of 300 Kelvin, such that its pressure is 2.02 times 10 to the 5th pascals. If the average kinetic energy of a molecule in the gas is to be A, tripled, and B, halved, by what factor must the RMS speed decrease or increase? In each case, state whether the RMS speed decreases or increases. Okay, I'm not entirely clear. I think the question's much simpler than it potentially could be made. So let's talk a little bit, guys. What happens here? I mean, there's a lot you can say regarding this. We could definitely play games with the N, the capital N, PV equals capital N KBT. PV equals capital N KBT. Wow, there's a lot you could do with that temperature. Temperature, absolute value temperature, is directly proportional, as we have already said, is directly proportional to kinetic energy. What does that mean? If you do everything else the same, if you increase the average kinetic energy of the particles, if there's the same amount of particles present, you don't change the amount of particles that are present. And you don't change the volume of the container. But what you do, let's say, is change the temperature and increase the absolute value temperature to a point where it's twice as big as what it was earlier. If it now is the size, if it's twice as large as what it was earlier, the pressure will be twice as large. Of interest. So if it's 3 times as much average kinetic energy per particle, everything else the same, and you kept the volume the same, you didn't change the volume, and you kept the number of particles the same, 3 times the average kinetic energy present would mean 3 times the absolute value temperature, period. 3 times the kinetic energy per particle is 3 times the temperature, absolute value-wise, that was there initially, then compared to what was there initially. That means there's 3 times the pressure if you kept the volume the same. If you have the kinetic energy, you have the absolute value temperature, and it's half as much pressure if you keep the volume the same. They're not going in that direction, but it's good to know, right? All that, like I said, all that kind of plays from this right here. And this equation almost cannot be overemphasized. Okay, we've already talked about them. They're connected. They're essentially the same equation, is what they essentially are. They're just written in a different manner. Pretty important stuff. Well, okay. Our big thing here, as far as the A aspect of this thing, we're talking about average, and let's not worry about the language so much. Kinetic energy final on average, you're going to make it 3 times the kinetic energy that it was initially, on average per particle. Let me just write it like that if you're okay with that. What does that mean? Well, that means this. That means 1/2, the mass of the particle stays the same. It's the same gas. The average of the squares of the VFs is going to equal 3 times that kinetic energy final. It's going to be 3 times that. Multiply by 2 on each side and divide by m. Yeah, the square, the average value of the square of the final situation, the average value of the squares of the final situation is 3 times the average value of the squares in the initial situation. What's going on here? Square root both sides, and I'll tell you what's going on. VF RMS is equal to the cube root of VI RMS. When you square root this guy, the VI, when you square root these averages, you get VI RMS. When you square root this guy, VF RMS. Okay, so pretty big conclusion here. Yeah, I go through chalk, guys. Like one of my other places of employment, I've been called the chalk man, so I feel like I'm some kind of a legend or something, right? In my own mind, I guess, right? But anyway, so the chalk man rides again. I'm going to have to get a little more chalk in a little bit here, guys, but let's see what we have. I think I got enough for now. The big thing is right here, guys. This settles a lot of stuff for us right here. If we get it to here, we're fine. For that. And that's essentially that's how the other one's going to play too, but it's just going to be like different numbers. So as far as like the ratios there, how are you going to do it? VF RMS over VI. Yeah, absolutely. What's the ratio? The faster one, if you're going to triple the average kinetic energy per particle, and that's what this is. The KF is 3 times what the KF is 3 times what the initial KE is. The KEF is 3 times the initial kinetic energy. If you want 3 times the initial kinetic energy finally present, you got to have 3 times the average kinetic energy per particle, which means that the root mean squared of the faster particle, the final the final situation, the particle in the final situation, the ratio of it compared to the initial situation in terms of speed, the speeds have a ratio of the square root of 3. Final speed divided by initial speed is the square root of 3. When you square those, you get the 3. 3 times more kinetic energy. For 3 times more kinetic energy, all other things kept the same. For 3 times more kinetic energy, if the speed of the final circumstance, the final situation is square root of 3 times more than the initial situation per particle on average, that's how you get it. Wow. If it's going the square root of 3 times faster than it was initially, that corresponds to 3 times the absolute value temperature. That corresponds to 3 times the absolute value temperature. And there's a whole bunch of things we can say. Once we start playing games like this, we can start putting things in here. And the pressure would be different too. Oh, sure it would. All of the things equal, it'd be 3 times the pressure. I already told you that. Okay? So that's it. I mean, it's essentially, you guys. This is the answer to part A on this thing. That's the answer to A. The answer to B is like the same exact argument. The same exact argument there, guys. Let me just see here. So for B, you're looking at KEF on average per particle. Now you want it to be a half. What does that mean? Well, I'm going through the similar song and dance that I've been going through. 1/2 MVF, the average of the MVF. So it's like an MVF squared, the average of it, the average of the squares, is half of the 1/2 M, the average of the VIs. The average thing is bothering you a little bit. You can kind of sort of ignore it and just say, well, 1/2 MVF squared equals 1/2 of 1/2 MVF squared, MVI squared. Same thing here. You could kind of just get rid of, I don't want you doing it, but I'm saying just to kind of give you a gut feeling, just saying, 1/2 MVF squared is 3 times 1/2 MVI squared. This is just the average of the squares, which is like some MVF, which is like some VF squared. It's actually VF RMS squared. The VF RMS is the average of the thing being squared. All right, so you get down to here, you guys. Well, the mathematics is the same. I'll tell you what I'm going to do. Why don't you divide, you can do this a bunch of ways. Why don't you divide by 1/2 m, divide by 1/2 m on each side. Square root both sides. When you square root the average of the squares, you get the RMS. You get the RMS average. The square root of VF, the square root of the average of the VF squareds, the square root of the average of the VF squares is VF RMS. The square root of this is 1 over the square root of 2 times VI RMS. If you divide by VI RMS, this is VF RMS. This is VI. There's a lot of ways you can write that. A lot of times mathematicians don't like to write a radical in the denominator, like to rationalize it. You can leave it as long as you're cognizant of of the ultimate mathematical reality that's present in this particular part of the problem. So you're coming to this, is what, to make a long story short, you guys. And there you go. The answer to the question on that one, guys, for 55. Let's go to 56. Problem 56. A box with volume capital V confines 18 particles with identical mass m. Each one has identical mass small m. And the following speeds. 3 particles are moving with speed v. 1 particle with speed 2v. 4 particles with speed 3v. 3 particles with speed 4v. 5 particles with speed 5v. And 2 particles with speed 6v. What are A, B, C? The following. What are the A, most probable speed, B, the average speed, C, RMS speed of the particles in this box? What's the most probable speed? Well, which one has the most frequently occurring speed is what they're saying. The one speed that you're most likely to get a hold of, a distinct speed that's there, which one are you most likely to get a hold of? Well, the one that occurs the most often is going to be the most probable speed. B, the average speed, just add them together and divide by the number of items there. C, the RMS speed. What is that? You're going to square each of the speeds. You're going to multiply by how often each one of those squares occurs. And when you add them all together, you're going to divide by the number of speeds that are present, how many particles are present, 18 of them. When you're done with all that, you're going to get square root. This is easier done than said. Let's just do it. All right, guys, 56. Make sure, guys, that the audio is going to last a while here. This thing is going down a little bit. We'll see. I should be able to go a little bit more before I turn it in. So looking at 56, you guys, we said a lot. I mean, how the question goes here, the most probable speed. The most probable speed is the most frequently occurring speed. Because 5 particles have speed 5v, 5v is the answer. So for A, the most probable speed, it doesn't mean, I mean, if like which speed is the most likely to be encountered. Now don't do any averages or anything. I want to know exactly, distinctly. These are discrete speeds. Which speed is most likely to be pulled out of the hat, so to speak? Well, the one that's most frequently present out of the 18 total. The most probable speed is the most frequently occurring speed. That is equal to 5v, because 5 particles. There are 5 particles that are going 5 times v. There are 5 particles that are going, now, the 5 has nothing to do with the 5 particles. There might be 20 particles, each one going 5 times v. But that's the most probable speed. Okay. The 5 has nothing to do with the 5 particle. It could be 20 particles, each one having speed 5v. This happens to have, out of the 18 particles, 5 out of the 18 particles have a speed of 5 times v. So that's the most, that's the one. The average V average is pretty straightforward. Just be careful with it, like anything else. Add all the speeds, and divide by the total number of particles present. What's that all about? Well, there's 3 particles traveling at speed v. I'll say that's 1v. There's 1 particle traveling at speed 2v. There's 4 particles traveling at speed 3v. That's a lot. Well, the one that took the cake was the one going fast. It was more than that. You'll see. There's 4 particles, each one traveling at 3 times v. There's 3 particles, each one traveling at 3 times v. And there is, let's see what we got here, guys. Let me exactly do this. Right, and there's 3 times 4v. And then this is the one that kind of took the cake for part A. There were 5 particles, each one traveling at 5v. There's 2 particles going real fast, 6v. And that was it. Divided by what? Divided by 18. Divided by 18. Okay. Interesting. I'm going to kind of I'm going to give you an idea. Some stuff we could talk about. I might want to leave that up there. It might be easier to kind of look at a bit. Look, let's get down to the business of what the heck this thing is. There's 3 particles traveling at 1v, 1 particle traveling at 2v, 4 particles, each one traveling at 3v, 3 particles, each one traveling at 4v, etc. 5 traveling at 5v. 2 traveling at this. Let's do a weighted average. There's got to be 18 particles. Well, what's 3 and 1? That's 4, and 4 is 8, and 3 is 11, and 5 is 16, and 2 is 18. Oh yeah, there's 18. There's 18. All right, what do we got here? Well, what we got is 3 times this is 3v. 3 times this is 3v. 1 times this is 2v. 3v and 2v is 5v. 4 times 3v is 12v. 12v and 5v is 17v. 17v. 3 times 4V is 12V. 12V and 17V is 29V. 29V. 5 times 5V is 25V. 25V and 29V is 54V. 54V. 2 times 6V is 12V. 12V and 54V is 66V. 66V, here's our weighted average, guys. 6 pulled out of here. Take a 6 out of here and put it into here. You got 11V. That goes into here. On average, that's how fast it's going. That's equal to the average. Roughly, it's 3.66 going on forever. That guy, well, that's that guy. The average is, it's that, which can be rounded to that. And that's B. And that's B. What about the root mean squared? Tell you what, let me use some of the data that's up there just as is. It might be a lot easier to go for it. So you saw the answer for B, you guys. Which is the same as this. Yeah, let's talk a little bit. Tell you what. Let's see, you know what we're getting here. 3.67 for the average. This is about right. It's a weighted average. Tell you what do you see is square each one of the items? That's going to be an average of the squares. That's going to be this. It's going to be the squares. It's going to be an average. The average of all the squares. What does that mean? I mean, take this guy, is what I mean. Take this guy and square it. Don't square the 3, just square him. 3 times this quantity squared. This quantity squared multiplied by 3. This quantity squared multiplied by 1. This quantity squared multiplied by 4. This quantity squared multiplied by 3. This quantity squared multiplied by 5. This quantity squared multiplied by 2. I'm going to get an average. I'm going to get an average of all the squares. What is that? Well, let's have a look. When you actually, if you actually do this, what you end up doing, this guy squared times 3 is 3v squared. This guy squared is 4v squared times 1 is 4v squared. This guy squared is 9v squared times 4. Okay, some significance there. 4v squared, the product 4v squared is 16v squared times 3. The quantity 5v squared is 25v squared times 5. The quantity 6v squared is 36v squared times this. Okay. Interesting. Well, 3 and 4 is 7. You know, we got v squareds all over the place, so we're not worried about that. We could factor the v squared out of there and just add the coefficients and we're fine. Okay? Then just have the v squared at the end. 3 plus 4 is 7, plus 36 is 43, plus 48 is 91, plus 125, right, is 216. 216 plus 72, 288. 288, the v squareds were tagging along all the way around, so they stay. It's that, so they stay, and you divide them by 18. We're not done. We did get to here. The average of all the squares, ladies and gentlemen. There's a lot of ways out of here. A lot of ways you could play this, actually. This 288 is 2 times 144. The 288 is 2 times 144. This is 2 times 9. The 2's cancel and you got 144 over 9. 9 goes into 144. If you tinker with it a bit, 9 goes into 144 16 times. If you square root the average of the squares, that's VRMS. And that's the square root of this. The square root of the product, 16V squared, yeah. Not too far off from like the classical average. The classic average was about 3.6 to 3.7, right? 3.67, 3 2/3. This is 4. The classical average, what better put, is about 3.6 to 3.7 times V, 3.67 V, 3 2/3 V. This is 4V. So in the ballpark, there's just two different kinds of averages that they're talking about. It is useful to be talking about an RMS average when you have squared quantities. Where do you have squared quantities? Just about every time you're talking about kinetic energy, you got squared quantities, don't you? Very often. So that's it. That's 56, you guys. Let's go to 58, 59, 61, and 62. Let's see how that proceeds. Let me just check on my microphone here after I erase. Guys, let me just put you on pause for 1 second, and then I'm going to come right back. Okay, guys. So let's see what we got here. We've got problem number 58. So I was able to straighten out the microphone, so that's good. So we should be okay to get through this. For problem number 58, they're saying the average translational kinetic energy and the RMS speed, the average translational kinetic energy and the RMS speed of molecules in a container of oxygen at a particular temperature are 6.20 times 10 to the negative 21 joules and 434 meters per second, respectively. What are the corresponding values when the temperature is doubled? Well, as we said, the average translational energy and the RMS speed of molecules in a container of oxygen at a particular temperature, and they gave us the values, the average translational kinetic energy per molecule and the RMS speed. What are the corresponding values if the temperature is doubled? If the temperature is doubled, we talked about a lot of things. The average kinetic energy would be doubled. If the average kinetic energy is doubled and all other things are held equal, the average velocity, the ratio of the squares would be a ratio of 2 to 1. The ratio of the square roots, the root mean squares, would be the square root of 2. Square root of 2 over 1. So let's see what's going on here, guys. This is kind of easier done than said, I guess you could say. They're telling us per particle, on average, we have the average kinetic energy per particle is 1/2 m, the RMS value of velocity squared. The average of the square, the average square velocity, 1/2 m times the average of the square velocities. 1/2 m times the average square velocity is the average translational kinetic energy that is present in the container. Per particle. They're not saying for the whole container as far as internal energy is concerned. Okay, and they are also telling us that the square root of the average of the squares, is VRMS, and they're telling us that's 434 meters per second. Okay, so they're telling us, we're getting this right off the bat, guys. Telling us this, and they're telling us this as a given. So, we know, we've already said this, temperature and kinetic energy, temperature and average kinetic energy per particle, temperature and average kinetic energy per particle are directly proportional to each other. If you double the temperature, you're doubling the average kinetic energy per particle. If you double the temperature, you're doubling the average kinetic energy per particle. If you make the temperature to a value 10 times what it was initially, the average kinetic energy per particle is 10 times what it was initially. If you drop the temperature to 1/5 of what it was initially, the kinetic energy drops to 1/5 of what it was initially. So on and so forth with that, guys. So we have this right here. So what can you say, guys? Basically what you're doing is you're doubling the average kinetic energy. So if that's the case, so for the question they're asking here, what's the kinetic energy final on average if the kinetic energy initial, and this was kinetic energy, this was kinetic energy initial, and that's this. Kinetic energy initial was this. So if you double that, be my guess, you're doubling what I had earlier. What is that? Well, you're doubling 6.2 rather, I'm sorry. You're doubling that. When you go for it, you got 12.4 Forgive me. No, I'm not wrong. Yeah, no, this is correct. Then you clean that up a little bit and you go 12.4 times 10 to the negative 21. That's the same as, in the more standard way to write scientific notation, you make that front value, the 12.4, make it 10 times bigger, make it 10 times smaller rather, so you end up making this guy on the tail end here 10 times bigger. 1/10 of this to get the value that it was initially, you got to make that 10 times bigger. So you got this. All right. So that's it. That's correct. That's certainly correct as an answer. But this is where they're coming from here, guys. At the end of the day on that. It's pretty straightforward stuff. We did this in some form or another in the past anyway, so it shouldn't be too bad for us. Yeah, we know that's true. Well, look, let's kind of keep playing that game then. I mean, if we're going to say that the final kinetic energy on average per molecule is twice as big as the initial kinetic energy on average per molecule, we've got 1/2 m VF squared. The averages of that is, that thing right there is actually twice as big as 1/2 MVI, the averages of that. Why don't you divide by the product 1/2 m on each side? Divide by the product 1/2 m on each side, you get V sub f squared, the average of the V sub f squareds. The average of the V sub f squareds equals 2 times the average of the V sub I squareds. Okay, let's square root both sides. If you square root the average of the squares, you've got the RMS average, VRMS. If you square root this, you got square root of 2. When you square root that, you get VI RMS. And that tells us a lot. I mean, that gets us to here. That's essentially the solution, you guys. Now we just got to plug in the appropriate values to actually get it. So I wrote it, I guess in my notation, I wrote the VF RMS, VI RMS. In my notes, I got VR RMS, VRMS F, VRMS I. Not a big deal, guys. So the way we had done it, let's kind of, to make it consistent with my notes, just in case there's any, I don't think it's really going to be an issue. Let me just stay consistent with the note. This is probably a better way to write it, the way I wrote it here, but neither here nor there. Let me just stay with some kind of consistency with the notes themselves and see what we can say about it. Okay, so we'll say VRMS F, VRMS I. And like I said, the initial way I wrote is probably better, but I'm trying to stay consistent with the notes. Well, what does that mean, guys, at the end of the day? At the end of everything that we're doing here, guys, we are going to look at this and say, well, if it's VRMS F equals square root of 2 VRMS I don't know what VRMS F is just yet, but I do know that's the square root of 2, and they did tell me 434 here. Square root of 2 times 434, and that's it. That ends the whole discussion on that. And yeah, the notation is not the big deal. At the end of the day, they want you to get the right answer here. It's got to be the square root. For you to get double the kinetic energy, you don't get double the speed. If you got double the speed, when you square double the speed, you got 4 times V squared. You get 4 times the kinetic energy. If you double the speed, 2V, the quantity 2V squared is 4V squared. That associated with kinetic energy is 4 times the kinetic energy. If you increase the speed to square root of 2 times the initial speed, when you square the square root of 2, you get the 2. That's where you get double the kinetic energy. So double the kinetic energy is going to happen here. And there it is. I mean, you're getting that, and it's good enough for us. So that's VRMS F is 613.77 meters per second, and the final kinetic energy being doubled is simply doubling the final kinetic energy. So these are the two questions they're asking there. Let me see. I don't even think that was an A or a B. I think it's just asked it flat out, and they said, okay, give me the answer. Put both in this one place. Looks pretty good. Looks pretty good. That's 58. Let's go to 59. 59, the average kinetic energy of an argon atom in a spherical container filled with argon atoms and with a volume of 1.0 times 10 to the negative 2 cubic meters is 4.50 times 10 to the negative 5. I'm sorry, 4.50 times 10 to the negative 21 joules. If the pressure inside the container is 2 atmospheres, how many moles of argon are in the container? Okay, pretty classic problem there, guys. Should be pretty straightforward as well. A lot of ways you could play it. Pretty relatively classic problem. Go, stay with the bread and butter of what we know. If we're faithful to the equations that we know, if we've looked at the equations, if we're comfortable how they are derived, and at the very least just comfortable with the equations on a sort of a gut feeling basis, we put those equations out there. We look at them and say, well, how can I apply those equations to this pretty standard type problem, which is what 59 actually is. So should not be too bad for us at all, you guys. Let me see here. All right, guys, like I said, for those who don't have the book, it's worth mentioning again. The average kinetic energy, for problem number 59, the average kinetic energy of an argon atom in a spherical container filled with argon gas and with a volume of 1.00 times 10 to the negative 2 cubic meters is 4.50 times 10 to the negative 21 joules. That's for one argon atom in that container. If the pressure inside the container is 2 atmospheres, how many moles of argon gas are in the container? Should be pretty straightforward, you guys. I think when we look at this, PV equals nRT, right? PV equals nRT, PV equals capital N, kBT. Man, T plays a huge role, doesn't it? It's kind of everywhere. So is pressure, so is volume. A lot of things are in there, guys, when it's all happening. They all got to be present. You're not going to contain a container without a volume. You're not going to contain substance without a volume. And if things are going on, pressure is going to be manifested if the temperature is there in one form or another, either increased or decreased or left as it is. There's a pressure present as well. There has to be particles present for pressure to be manifested, and for the temperature itself, I guess, at least for the particles to have a temperature, the particles have to actually be there. So there's stuff we have seen. We know how to do it, guys. We've seen the PV equals nRT. We've talked about it very much already. and we've got PV equals capital N K sub B T. T in both instances is absolute temperature. We have seen in the past, working with this stuff, talked about a lot of things we could say here. Now, we've done derivations in the past. Let me kind of just jump there. Let me not redo a derivation, I guess you could say. But we could say that I just want to make sure we can say a couple things okay here, guys, when we got this. Remember, we were talking about a number of things that we've done in past derivations. So let me just kind of go there. You guys have the notes for the past derivations on paper and on film. So let me just go to what we already have done. We have said this, that V right here is volume. I'm trying to make it big for volume. The average of the squares, and okay, you've heard these speeches before. Yeah, I mean, it makes sense how it all happens. We can actually, I'm just trying to figure out a way I can kind of maybe tell it to you in another way here. We understand that this 2/3 has manifested itself in the past. We have seen, remember when things go back and forth, we were getting the V squared. We were getting the MV squared, and we put the 1/2 here, so that's why we put the 2. The 3 manifested itself because there were the particles on average, their component of striking their components of striking the side of the container were 1/3, roughly equally the square components, I guess you could even say, the velocity components, the square components, 1/3 of the given velocity as it impacted, or of the square velocity, as we could say, the averages of the squares, I guess, be a better way to put it, was associated with the number 3. Remember when we had said that right there was V sub x squared plus V sub y. This is past derivation. We're not. I'm not regretting showing it to you again, but I'm not going to do the whole derivation again. But we've seen something like this. Remember, we said as far as the magnitude on average, the VRMS average, the average of these squares. I mean, typically it's looking like this. The average of this, the average of the squares, you guys, was. Okay, let's see here. The average of the squares. So, in a sense, I'm saying they're roughly equal in that direction. Sure, if that's the case, each one of these guys is just, and like I said, you really should put a bar over it. Let me not put a bar over it. Let's just say, okay, whatever it may happen to be, that's this kind of manifests what that really is. So what I got here is this is as big as that, and this is as big as that. And when we had done it, you added those together, you got that. The Vx squared was 1/3 V squared. The average square of the Vx, the average square of the Vx is 1/3 the average square of the velocity component in any direction. The average component of velocity, before you resolve it into x components, y components, or z components, the average component of velocity, the RMS component of velocity, unresolved, squared, 1/3 of it would give you, on average, what the Vx component is per particle. It would give 1/3 of it would give you the average of the Vx component. 1/3 of the total, 1/3 of the average velocity, 1/3 of the square of the RMS, 1/3 of the square of the RMS is equal to what the x component RMS squared of Vx is and Vy. Another way you can say it is 1/3 of the particles, 1/3 of the particles are colliding with the wall in the x direction at any given moment. Another third are colliding with the wall at any given moment in the y direction. So in the x direction, so to speak, 1/3 of the particles are colliding full on force, full on with the areas that are encountered in the x direction, the two areas that are encountered in the x direction, and the two areas that are encountered in the y direction, they're getting another third of the particles are hitting those. And in the z direction, those two areas that are to be encountered there, 1/3 of the particles are encountering those. And they're encountering them full on. Full on. This right here, if you say 1/3 of them. If you say all of them, then all of them, each one of all of them, 1/3 of this is hitting. So you can kind of look at it and say, everybody, a big number, true, 1/3 of all the particles are hitting with that big number. Or 1/3 of all the particles are hitting with that big number. Or all of the particles are hitting with 1/3 of that big number. Two ways you can look at it. I've kind of gone into that in the past. Okay. For our purposes, we're not, but that's kind of where that's coming from. And the two right here came out because there was not a 1/2 over here. There was not a half and not a 2, just the 3 underneath. Either 1/3 of all the particles colliding very, very hard in the x direction, or 1/3 colliding very hard in the y direction, or 1/3 colliding very hard in the z direction. Or all of them with 1/3 of the square average. All of them with 1/3 of the square velocity magnitude average. All of them are hitting with 1/3. All hitting with 1/3 this big number, or 1/3 of the numbers hitting with that max value. Notice it's the same value. So all of the particles, and then resolve them sort of in a vector sense. All of the particles are kind of like, well, they're all going to hit at 1/3 the maximum square, or the average square. The average square of of an unresolved speed, the average of that square, 1/3 the magnitude of that is what every single particle is going to hit with in the x direction. All n of them are going to hit. Yeah, but each one with 1/3 the speed. 1/3 the square speed, if it's all of them. Or it's just 1/3, 1/3, 1/3, but each one hits max. Either way, the numbers here come out the same. These two are equal to each other. So it's a way you can kind of look at it. Pretty interesting how that goes. As we said, when the first numbers were coming up, that simply wasn't present, nor was that, but the third was there. And that's where that's coming from. Okay. Anyway, you've seen the derivation. Hopefully that means something, guys. The big thing here is it's true, and let's see what we can do about it. Now remember, when you square something, how do you get it to be a third the size? If the square of something divided by 3 is an answer you want to get, what would you square to get v squared over 3? It would be v over the square root of 3. So the velocity would be the square root of 3 times smaller than what it was the other way. Okay. all of that, like I said, it's neither here nor there on that. We've seen this stuff already. This is the bread and butter, ladies and gentlemen, with which we start. We have derived things up to here, and that's pretty important stuff, because now we can say a bunch of things about it. We can say, okay, if this is the truth on something like this, can you solve for n? Yeah, sure I can. What I can do here is, I can do a whole bunch of things here, actually, is what we can do. You can look at it and you could say, I might even go against some of what I had already said. A half times 2/3 is a third. What do you say, a half times 2/3 is a third. Let me multiply by 3 on each side. Let me multiply by v on each side. Let me just write this a little differently than what I had done. 3, there's n. Let me divide by mv squared, and that'll give you n. Now you could have said, hey, look, Jim, I prefer, you maybe would have kept things a little differently. There's where it comes to, guys. Something like this. Perhaps it's a little more intuitive. This is true, nothing wrong with this. Perhaps it's a little more intuitive if you'd have just kept it as is and said, hey, look, man, let me multiply by v on each side, and then multiply by 3 halves. So this 3 halves PV is pretty significant. And this is the kinetic energy that is present, and then you divide by 1/2. mv squared, half here, like that. That's pretty neat, because that's really, there's a lot going on there. What you got is, yeah, there's a whole lot going on is what there is. We've got essentially 1/2 mv squared per particle. There's a lot of particles, capital N. If there were a lot of particles, you'd have this, and you'd have this. Yeah, I know, but if for one particle, divide by capital N, and you got kBT. True. And, and that's of interest. So you got that. And the other one, three halves PV is 3 halves nRT. That's total. That's very interesting. That's the total internal energy. Wait a minute, something going on here, guys. If this is the total internal energy that we talked about in another video, another discussion, in another place, note somewhere else, we see it in the book as well, as far as translational kinetic energy is concerned. What they had actually said here, like I said, they've got an argon, okay, we got, so, you see here, guys, make sure it's one of the, this comes at us. This comes at us in an interesting manner. That's for sure. We can say this is the total internal energy of what is going on of the system. If you divide it by the internal energy of one of these, you should know how many there are. In a sense, we're looking at this. Just trying to think here, guys, for a second. If you're looking at what's going on there, let me just see what the total energy of the system would be. You got this, and then you got 3 degrees of freedom. Well, that would take place. There's where your 3/2 comes into play. I just, to me, what just jumps out is if that's the total internal energy, and this is the energy of one of them, the energy per one going into the total energy will tell you how many items are present. That's all that's going on, you guys. In this sense right here, what happens is this right here is total internal energy. And let me just see here. I want to see if I... Yeah, I mean, this right here is nRT, and this right here is going to be the kBT. Something along those lines of what we're going to say here. Now, there's a lot more that comes into this, guys, but it's something along these lines of what's going on here. You got this, and you got the average kinetic energy per particle. That's the kBT. It should come out. I think the 3 manifests itself in a place that we're not used to seeing it. 3/2 like that because it's the 3 degrees of freedom. But it's coming along around those lines, you guys. You're going to do something like this. So this is what we're looking at here. And let me kind of see where it's going to go. I mean, you can say that. Trying to just argue with myself here where it had gone. Yeah, the 3 was manifest in terms of what we are seeing here, because you got to have all of that present. It's fine. This should actually get you there. Either one of these should get you there regarding what was present. Now, yeah, PV is 2/3 that. So we were saying how the pressure was manifested. The pressure is from 1/3 that size, so that's where that would have to come from. So this is roughly where it's going to take place, you guys. I think the way we would have to look at it. For the average, it sure looks like it, but there's the 2/3 there. There's the 3/2. I think there's the 3/2 that would have to come in here as well, you guys, for that whole process. If that was 3/2 PV, this is going to be something on the order of 3/2 right here as well. Okay, I don't want to. So somewhere along these lines, we're getting what we're talking about. And if you multiply by all of those, you'd get a lot of what's going on. So this would go, these would cancel, these would cancel, the NR, and I don't want to, I'm probably spending a little more time with this than I should be doing. The KB, we said was Avogadro's number, was R over Avogadro's number. Should I say here it was R divided by Avogadro's number? Yeah, so this right, the KB is R divided by Avogadro's number. That is what KB is. This is NR. The R's cancel. You end up getting number of moles times Avogadro's number. You get capital N. Okay. Forgive the mathematical gymnastics there, guys. If we're going to call this guy 3/2 PV, then it's 3/2 NRT. 3/2 PV is 3/2 capital N, kBT. So on and so forth. So let's stay just with this, guys. The numbers work out. You got to be a little careful here. Again, I'm perhaps ill-advised going back to another video on that, but we've gone into this in some manner or another already up to this point, so we don't have to prove it, but I want to give you at least some structure to it. You're looking at this right here. These are identical. This doesn't have the same meaning that has. They're saying basically if the total energy of the system is 3/2 PV, which is 3/2 nRT. That's because PV equals nRT. 3/2 PV is 3/2 nRT. You got this. True. And that's the same as 3/2 PV, which is capital N kBT. And this is stuff we've derived before, guys. So let's not go back there. We just go back to our notes if we want to look at it a little bit more. MV squared. Yeah, that's of interest. I mean, so something like that happens, you can look at where that's going to go, you guys. So you say, okay, what about it? So you got 1/2 MV squared on average. You got this, and that's where a lot of this stuff is going. That when those cancel, when the halves cancel, you got 3 PV MV squared right there. Look at like a negative here. That's a square, and then there's that. Okay. So on and so forth. This is the total energy in the system. This is what is happening per particle. How many times if this is the energy per particle and this is the total energy that is present, per particle, you got 3 kB, 3/2 kBT times N per particle on average. And every particle's got this. Every particle's got this much kinetic energy, which is the same as this, 3/2 kBT. So that's what I was saying. I had the 3/2 a little bit off there on that. But that's it. These cancel. In the end, you're going to get N. And then from there, we can find the moles. Well, let's find what we can say, guys. I mean, you're looking at this thing. You can say, depends where you want to go. Now, here's the problem. Nobody gave you the temperature. I mean, we could find the temperature. We know enough to find the temperature, but this right here will get us right where we need to go. So let's talk. Capital N. May I say that capital N, well, let's not say anything yet. Well, no, let's say this. Let's say capital N is the number of moles times Avogadro's number. And that's equal to 3/2 PV over 1/2 M that 3/2 was something, guys, I ignored it earlier. Forgive me. We caught it. We caught ourselves. We ignored it earlier. It's present in the derivations that we were doing. We found this out earlier in the derivations that we've talked about. So it's there. We know how to do it. This is the total energy. This is the total energy, and this is the energy in just one of them. Well, if you get the energy that's in just one of them, and you put it into the total energy, however many times the energy that's in one fits into the total energy, that'll tell you on average how many particles are present. The total energy of all capital N particles is this. divided by that small amount of energy in just one particle, how many times does that small amount of energy fit into this big amount of energy? The number of times that it does tells you how many particles you need to get this big energy. That's based on stuff we talked earlier. And that's what all that's about. Well, they didn't give us all of that specifically, but they did give us enough to get here. They did give us enough to get here. So, we've been there, we've done that, and all of this is that we do, comes back to starting here and also starting with the phenomenon of billiard balls colliding all over the place, these small, tiny spherical balls flying all over the place, billiard balls flying all over the place in the container, and you could say a third of them are going along the x-axis, a third are going along the y-axis, and a third are going along the z-axis, and they're full on speed if you go a third in the x direction, a third in the y direction, and a third in the z direction. So z direction, x direction, y directions, a third of capital N in each one of those directions, going full RMS speed squared. Full RMS speed in that direction, hitting the wall in that particular manner, straight on. That's what we can say, and so the RMS squared is just the average of the squared. Or you can say, no, I think all of them are hitting in one way or another in the x direction eventually, and in the y direction eventually, and in the z direction. But if we're going to do that mathematical thinking, a third of the square is what's being manifested. VRMS over the square root of 3 is being manifested in those directions if all of them are involved. That's what I said earlier. Okay. Well, the big thing here, guys, is you've got this. So let's see what you can do. It's all I did, guys, was take this and write capital N as the number of moles times Avogadro's number. And we got this. Well, we got anything. I mean, this right here stays. This right here is what that is, exactly. The number of particles present is the number of moles present times Avogadro's number. Fair enough. Take and divide the top one by capital N sub A. And we got 3/2 PV over Avogadro's number, and the 1/2 mv squared is just for a single particle. Okay, let's go. Okay, let's deal with it. They told us, well, we know 3/2 is 3/2. They told us the pressure is 2 atmospheres. What's that? Well, there's 2 of these atmospheres. Each one is 1.013 times 10 to the 5th pascals. Okay, I just didn't write down pascal. I don't write down the units. But that's pascals. The volume is 1 times 10 to the negative 2 cubic meters. Okay. They are telling us that Avogadro, well, we already know Avogadro's number is 6.02 times 10 to the 23rd. They might use 6.022. It's not going to be a big deal, guys. This 1/2 mv squared is the average of just one of them. That's what the 1/2 is, guys. That's what the 1/2 mv squared is, rather. You got Avogadro's number there. Let me see. Yeah, it should be on the mark, guys. Let me just 59 here at the end of the day. We're getting 1.12 moles. Yeah, I think so. I mean, let's confirm it. This, I mean, like I said, I got a bit adventurous with this problem. It would have been done about 10 minutes ago, easily 10, 15 minutes ago, if I hadn't thrown this in here. But I think it's worthwhile stuff. I mean, the 3/2 is manifested in the derivations. I didn't have it in there initially, and it created some problems. Once the 3/2 is manifested in the derivations that we've done, it arose here, it arose in some other places. Here more than anywhere, it arose right here. It almost can't be emphasized how important that is. In earlier work that we have done, I think I've done this I know I've done this on at least one video, maybe two. We were already here and we already did this. So this is something that this is something we've seen before. So we deal with that, and that's why we're getting these numbers. And these numbers speak to regarding total energy compared to the energy of just one particle. And if you divide the energy of one particle into the total energy, you'll find the total number of particles. That's the argument here. Forgive the long-windedness of it, but that's the way you'd want to go. Let me just confirm this to be sure, guys. I don't want to see this be something too crazy for us here. Just quickly confirm this. Uh, 10 to the 23 times 10 to the negative 21 is 10 to the 2. 10 to the 23 times 10 to the negative 21 is 10 to the 2. 10 to the 2 goes into 10 to the 5. 10 to the 2 goes into 10 to the 5, 10 to the 3 times. 10 to the 3 times 10 to the negative 2 is 10 to the 1, just 10. So 10 times bigger than what I got right here. If that's the case, just be formal about it, guys. I got 1.1218, 1.121816, 168 something. So 1.12. That's about right. That's fine. That's fine. Again, guys, the big, probably the easiest way to do this, especially if you're pressed for time on a homework assignment, obviously, or certainly on an exam, is just say, look, we know this is the bread and butter. The bread and butter of what to look at, how to proceed. We've also seen derivations of how we can look at what happens at the microscopic level and draw some very interesting conclusions related to these two beautiful equations. Well, these two beautiful equations are actually one and the same. They're just kind of written separately to describe the phenomenon that are taking place, but they're really, one is born of the other, in a sense. We use this one for macroscopic phenomenon, and we saw that, hey, we can microscopically kind of see how it relates to a microscopic view of what's happening there, the actual particles hitting. So two very important equations, essentially the same equation is what they are, and then from there we can derive from what we know about kinematics, derive this. And from here, once you've gotten here, you can solve for capital N is what you can do at that point. Once you got this, just solve for capital N, you're right here. You could also say that. This is a little more illustrative of what's happening here. Total energy present, 3/2 nRT. We've seen that before. That's the internal energy. 3/2 nRT. Well, it's there, okay. 3/2 nRT. 3 halves nRT is the same as 3 halves capital N K sub B T divided by the energy per particle. And that's where we're getting the total number of particles. When you take the total number of particles and divide it by Avogadro's number, you get the moles. And that's where it's coming from. Okay. I hope that helps. With that in mind, guys, let's look at 61 and 62. Well, okay, here we go. I mean, it's speak of the devil, guys. It's what we were just saying came up and is looking right at us, I guess. Problem number 61. The total translational kinetic energy of hydrogen molecules contained in a sealed 10-liter container is 7.5 times 10 to the third joules. Determine the pressure of the gas. Hint, use equation 21.2. NK average, capital N K average equals 3 halves NKBT. Okay. They are saying what we just said. So let's go. Let's do it. 61 and 62. Let me erase everything, even that right there. I guess we got 2 more problems to do, and that'll be it for that. So let's do 61 and 62, guys. Again, where this stuff arose from, we said it was from the conservation, I guess you'd say it was from the conservation of momentum in a perfectly elastic collision. And then when we divided it by time, but when we created the time, when we talked about how we could write time was equal to what? D divided by V. Distance traveled divided by magnitude of velocity. Distance traveled divided by magnitude of velocity will give me time. And that's where the V squared got in there. There was an MV squared in there wasn't a half. We put the half in there, but then we had to multiply by 2. We divided by 3 because, as we said, a third of the particles one way in the x direction, a third of the particles the other way in the y direction, a third of the particles the other way in the z direction, or we could just say they're all doing it, but at 1/3 the speed, 1/3 the average square speed, 1/3 the average square speed. So 1/3 the average square speed, 1/3 of the average square speed in all of the particles, or a third of the particles, each one with the full average square speed. That's where it came from. That's where the 2/3 came from. And later on, the reciprocal of 2/3 was the 3 halves. And that's where we're getting 3 halves in those equations, you guys. So for 61 and 62, they are saying, again, for those of you who don't have the book, this is hopefully intended for anybody, guys, who wants to look at it. The total translational kinetic energy of hydrogen molecules contained in a sealed 10-liter container is 7.5 times 10 to the third joules. That's 7,500 joules. Determine the pressure of the gas molecules. Simple question. They're saying NK average is equal to 3 halves NKBT. That 3 halves, that's what we just talked about, right? That's something, we've seen that before. Like I said, when I was doing the derivation, following closely the brilliant work of other people that have done the derivation before I was doing it, right? Following their brilliant work, when you saw me look at that derivation, that's where the 2/3 and 3 halves are coming from in these equations pertaining to this stuff. Okay. With that in mind, we'll just look at what we know, on this and figure out what they need. Is it true? Well, I mean, through various songs and dances that we've done in previous videos, we know this is true. From what the book brilliantly teaches us, from what Dr. Katz brilliantly teaches us, and what other people have, and the survey has brilliantly taught us, and other people have brilliantly taught us, guys, we know this is true. We've seen this. We've seen this in at least one video that I've presented already, following those great scholars who knew this stuff very well. All right, so we know that. If we know that, what do you want to say? Well, how about this? How about we take, they say, take the 2, take the 3 on the bottom, take the V on the bottom, and move the N over here inside. All right, so what you're trying to say is you got this. Okay, that's fine. So look, let's kind of do something related to the total translational kinetic energy. And there's other aspects that go into internal energy. So it's not, you know, the 3 halves works great when you're talking about a monatomic molecule. But, you know, there's different degrees of freedom that come into play, so other coefficients can come up also. But still, I mean, by the equal partition theorem, if it's on average 1/2 nRT and there's 3 degrees of freedom, there's 3 halves nRT for all 3 directions. And if there's spin one way and spin another way, that's another 1/2 nRT and another 1/2 nRT, and it's 5 halves nRT, et cetera, et cetera. So there's ways we can do this. Right now, guys, this right here is the total, is the KE translational total. So what we have here is pressure is equal to KE. This is all each particle's got this much kinetic energy, and there's n particles. This is KE, total translational. Yes, okay. Kind of interesting how that comes into play. The 2 came out there because we didn't have a half associated with this. So there's, and the 3 on the bottom, because you don't, the particles are going, it's just, not all the particles all at once are hitting just 2 walls. All the particles all at once are hitting all 6 walls. A third of the particles roughly are hitting the x direction walls. A third of the particles the y direction walls, and a third of the particles the z direction walls. So I think the 3's in there. That comes into play based on stuff I've already said. All right, so it shouldn't be too bad. What we're looking at is 2, 3. And what you got here, they're saying it's 10 liters. Yeah, 10 liters are 1,000 cubic centimeters. 1 liter is 1,000 milliliters. 1 liter is 1,000 milliliters, and every milliliter is 1 cubic centimeter. 1,000 cubic centimeters is a liter. 1,000 cubic centimeters is a liter, and there's 1,000,000 cubic centimeters in a square meter. So 1 liter per 1 cubic meter is equal to 1,000 over 1,000,000 is 1,000th. 1 liter is 1,000th of a cubic meter. Okay. So that's it. I mean, so 1 liter per 1 cubic meter is a ratio of 1 over 1,000 as far as actual volume. So 10 liters are equal to, so I guess the way you want to look at it is, the way you can, if you multiply by 1,000 on each side, you get 1 cubic meter is 1,000 liters. So what are we talking about here, guys? We're saying every cubic meter is 1,000 liters. And if you got 10 liters, that's 1 times 10 to the negative 2 and that's where they're getting that. There's 10 of them, right, 1 times 10 to the negative 2. So in other words, you're multiplying this right here. That's 1,000th. 10 liters is equal to 10 times 10 to the negative 3 cubic meters. That's 10 to the negative 2 cubic meters. That's where we're getting that, you guys. So you can write that a bunch of ways, guys. So the way we did it, the way I did it was 10 liters. Each liter is 1,000th of a cubic meter. Each liter is 1,000th. Each liter is 1,000th of a cubic meter. There's 10 liters. 2 over 3 V. That's that. They are telling us, okay, for some reason here, I just want to make sure we are in agreement here. The total translational kinetic energy of hydrogen molecules contained in a container is this. That's straight out. There's no 3/2 or 2/3 on that one, guys. This one's just flat out what it is. This is n times 1/2, which is, well, we don't know. We know that the total here, the n times 1/2, is going to be 7.5 times 10 to the 3 joules. And that's it. That's the end of the day on that, you guys. That's the way that thing's going. This is 10 to the negative 2. Divide something by 10 to the negative 2 is like multiplying by 100. 3 goes into here 2.5 times. 2.5 times 10 to the 3 times 100 is 2.5. 2.5 times 10 to the 2 times 10 to the 3 is 2.5 times 10 to the 5 times 2 is 5.0 times 10 to the 5 pascals. Let's see what we got here. Yeah, there it is. So either way, you grind out the numbers, guys, you should be okay. So that's the total energy of the system. There's other things that were going on, you guys. I do have to say this. I mean, forgive me. I mean, in terms of total translational energy, that might not mean the total, that may not mean the total internal energy. You know, there's other things that come into play for the total internal energy to that come into play. There's rotation, there's vibration, there's rotation in different directions, and vibrational motion in directions as well that could be happening. So we're talking about Hooke's law in a sense for the oscillatory motion, vibrational motion, way vibrational energy is stored and manifested, and the way rotational kinetic energy is stored, and that's different from translational kinetic energy. So the total of what goes on there could be kind of interesting how they're actually talking about that. So we can say this kind of thing, guys. There's a lot that happens, but we know how to actually do that. We know how to actually say stuff like this. If we are right, exactly. There's a number of ways it can be looked at. So there's where we're coming from at the end of that. I think that's it. I think that's where we're going to go with that. Again, it's always tempting to want to go back and rederive this stuff. With the right book and the right notes, you guys, we go back to it quite easily. We did it before. We can do it again if we have to, but we're fine. We can stop right there and be okay with this whole thing. So 500,000 pascals of pressure in relation to translational kinetic energy. That may not be the only thing that's going on here. But what you can say here, guys, is, you look at this and there's just some fascinating stuff that you can say. You could take the PV here, and I think, this is, worthwhile at this point. We've said this was somewhere, and how we can find it. We've derived it. We've talked about various things. Is it believable? What's going on here? Well, if you multiplied by V on each side, you got PV. Then I got this 2/3 going on here. Then I got all this. Okay. So that's pretty fascinating. If you multiply by 3 halves on each side. Yeah, this is where it goes. I mean, for a monatomic gas, you've got this right here. Well, what is that? This right here is 3 halves nRT. That's what it is. 3 halves nRT. I had failed to put the 3 halves in there at some point somewhere, just recently, not in the big derivation. The big derivation, we derived it just fine. But this is 3 halves PV. What is that? Well, this is PV, right? And when we say 3 halves PV, that's 3 halves nRT. That's the total internal energy of the gas. If it's monatomic, just spinning, what the heck is that? That's every single particle accounted for, multiplied by the average kinetic energy per particle. Wow. That's where that 3 halves nRT came from. Well, isn't N the same as number of particles divided by Avogadro's number? Number of N moles is number of particles divided by Avogadro's number. Avogadro's number into R is Kb. That's N. Here's your Kb, and here's T. 3 halves KBT, 3 halves nRT, and this is kind of what I was trying to say earlier, without the greatest success. But that 3 halves, it's not just, it's something, once we've done the derivations, this right here, this, in one direction, it's 1/2. In one of the directions, it's 1/2 capital N kBT. In one direction, it's 1/2 nRT. Yeah, there's 3 directions though, guys. What's 3 times 1/2? Because you're not getting everything manifested in one direction. Only 1/3 of the internal energy is being manifested in one direction. There's another 2 directions. So a total of 3 directions where it's being manifested. So 3 times 1/2 is 3 halves. And that, there it is. That's very important. That's very important. Go to 62. 62, a 0.500 meter cubed container is filled with 30 moles of carbon dioxide gas, CO2, such that its pressure is 2 atmospheres. What is the RMS speed of the molecules in the gas? PV plays a huge role, guys. That PV, remember, pressure times volume is in units of energy. You could almost argue for an ideal gas, half of that PV is on average what goes on in one direction. Then take care of the other 2 directions, a total of 3 directions, 3 halves PV. It's a good way maybe to at least maybe remember it. But again, the math doesn't lie. We gave derivations pertaining to that. And it went fine. All right, a while ago, so we can always go back to that, either in the book and or the videos and or the notes that we have, but it's all there. Pretty fascinating stuff, how it all boils down to motion. You're talking about internal energy, and in the end, we're talking about motion, even at that small level, even at the atomic level. The atoms are moving. How fast? Well, the faster they're moving, the more energy involved. The more energy has been given to them for them to move that fast. The more degrees of freedom that they have, well, that's an issue too. If there's a lot of degrees of freedom, it's going to be hard. If you want to get them to a very high temperature, there's a lot of energy you got to put in there because a lot of degrees of freedom have to be accounted for, have to be filled if they're active degrees of freedom. Okay. Anyway, fascinating stuff, how it all does come down to the motion that we've already talked about earlier in this course. Pretty fascinating stuff in that regard. What is the RMS speed of the molecules in the gas? Should be pretty straightforward for us, guys. All right, guys, 62. At least 2 ways to look at this, and they both are closely related. There's method 1, method 2. Well, tell you what, let me quickly do it. Let me try to quickly do it. I don't want to burden you too much more than I already have. Method 1, tell you what I'm going to do. The number of particles that are present is equal to the number of moles times Avogadro's number. There's a lot of moles present, guys. There's 30 moles present, and Avogadro's number, 6.022. Just watch out how they want you to use that number, when they want you to use it. The number of particles present is 30 times Avogadro's number, which is 180.66 times 10 to the 23rd. Let me write it that way, if you don't mind. Please let me write it that way. You could write it 1.8066 times 10 to the 25th, but I'd like to keep that some aspect of that famous Avogadro's number on there. Just make sure it's 30 times bigger, and there it is. They talk about pressure. Pressure, huh? There's 2 atmospheres, guys. 1 atmosphere of pressure is 1.013 times 10 to the 5th. Pressure is 2.026 times 10 to the 5th. All right, let's just kind of see where we are. Okay, now what? Well, look, at the end of the day, you guys are asking how many, they're going to ask us here, what is the RMS speed of the molecules in the gas? Tell you what. Yeah, this is like the 3rd problem we're looking at this thing. Luckily, we derived this a while ago. That's volume. Okay, that's volume right there. This is velocity or magnitude of velocity. Small v, big difference, okay? We derived this a long time ago, so we can do it. We know how to do it. We derived it a long time ago. We look at this and say, what do you want to talk about? I think the hardest part of this whole thing has just been derived. If you look right here, I'm looking for the RMS speed. Why don't I just solve for v squared, you guys? Why don't I just solve for v squared? Take this guy and get him all by himself. Well, let's go. Let's deal with it. I guess were we told the volume? Were we told? There's the stuff we were told, the stuff we were not told. They told us the volume. They told us the number of moles. They told us the atmospheres. They told us. I think we're good. We got to look up carbon dioxide, and I think we're okay. Only translational kinetic energy is going to contribute to the pressure. However, to get something to go to a particular temperature, to have it manifest a big pressure, a lot of energy has to be put into it if it's a complicated molecule. Even though only translational energy is going to account for it, to get it to that temperature, I don't know, let's say temperature 500 Kelvin. It's easier to do that with a monatomic molecule that's light than it is to do it with a heavy molecule. No, I take that back. That's not an issue. The issue is, if it's a complicated molecule, there's going to be other aspects of what goes on with that molecule in terms of stretching and compression, the vibrational motion, rotational motion. There's a number of things that can happen, and you've got to fit, by the equal partition theorem, all the degrees of freedom have to be paid, in a sense. Energy is going to go, by the equal partition theorem, into all the active degrees of freedom. And that requires more energy than doing it to something simple, a simple particle, monatomic particle. Okay. Well, let's talk about this. This is a relatively complicated particle. They told us enough. We care about the translational energy in this regard. They are telling us that's about it. They didn't tell us the temperature, but they told us enough we could find the temperature if we had to. Look, let's just make a long story short. You take this right here, the average of the v squareds, and let's get down to business. the 2/3, I did this last time, and then I kind of went against it, but now we can do it. I mean, it's the same answer at the end. 2/3 of a half, that's basically what it is. 2/3 of a half, or half of 2/3, is a third. So it's going to come out to this guy, M. Forgive me, no. Let's leave it. Yeah, let me kind of make it. Hopefully, this is a good decision. 2/3 of a half, or half of 2/3 is a third. Half of 2/3 is a third. Let's go. Let's solve for the v squared bar. Multiply by 3v on each side. Divide by capital N times m. That's kind of interesting. That is interesting. The number of particles times the mass of each particle will tell you the mass of the entire gas that is present there. The entire mass of the material, of the matter, the entire mass of the matter that is present there will be told right here. If it's 30 moles, if you knew the molar mass, the mass per mole of carbon dioxide, and you multiplied it by 30 moles, yeah. What's the mass of carbon dioxide? Well, let's see here. Carbon's got 12 atomic units of mass. Oxygen's got 16, and there's 2 of those oxygens. 16 and 12 is 44. 44 atomic mass units. 44 atomic mass units, that's 44 grams per mole. There's 30 moles. 30 moles times 44 grams per mole is 1,320 grams. 1,320 grams, 1,320 grams is 1.32 kilograms. 1.32 kilograms. This is 3. This is the pressure that we already discovered. This is the volume. And you know what? You can actually go that way. You can actually go that way. And I showed, I don't know, I'm not sure exactly how I want to go here with that, but there's a couple, I'm going to get the same answer either way. Let me kind of throw the dice on this one, guys. I didn't do it the way I just told you, but this is certainly true. Why wouldn't it be true? If you got this here, and you take and you square root it, that's VRMS. That's the square root of all this. Now, look. This is the mass of one carbon dioxide molecule. One carbon dioxide molecule, CO2. CO2 is 12 plus 16 plus 16 is 44 atomic mass units. 44 atomic mass units means it's 44 grams per mole. We go back to our chemistry. 44 grams per mole, 44 grams per mole times 30 moles is 1.32 kilograms. You could play this a whole bunch of ways. Just go for it. They're telling us, I'm thinking it's this. This is not the way I initially did it. You guys can see my notes on that. 2.026 times 10 to the 5th. 2.026 times 10 to the 5th. Yes, I'm getting more chalk. I get called the chalk man for a reason. 2.026 times 10 to the fifth. V is, they told us what V was, I think. I could have sworn they did, and I just didn't write it down. There it is, yeah, 0.5 cubic meters. The mass of one carbon dioxide molecule times the number of molecules. Well, I can do that. I can find out what the mass of one, you can do it another way. We said CO2, 12 for carbon, 16 for oxygen, 16 for the other oxygen, adds up to 44 atomic mass units. Multiply that by 1.66 times 10 to the negative 27. And then multiply it, multiply that by 30 moles. Multiply that by this many particles. 180.66 times 10 to the 23rd particles, times, like I said, I'm going just on what they said. I said 10 to the 27th. I hope I'm right. Yeah, right. 1.66, yeah, something like that. 1.66 times 10 to the negative 27. You could do this. You could say, hey, look, man, there's 30 moles. Each mole has 6.022 times 10 to the 23rd molecules. Each molecule has an atomic mass of 12 plus 16 plus 16, 12 atomic mass units for carbon, 16 atomic mass units for each one of the two oxygen molecules. This times 1.66 times 10 to the 27th. And that's going to tell you the total mass. That's going to tell you what capital N, the number of particles, times the mass is. Well, I said it was 1,320 grams, 1.32 kilograms. These are in kilograms. They kilogram, it's the MKS system of units, guys. So they're going to make it kilograms. Let's just see it. Here it goes. So 30 times 6.022 is the 180.66 we talked about. Times 44 times 1.66 10 to the 23rd times 10 to the negative 27 is 10 to the negative 4. So divide by 10 to the 23rd times 10 to the negative 27 is 10 to the negative 4. Multiplying by 10 to the negative 4 is the same as dividing by 10,000. I got 1.3195. 1.3195, 4 times 10. Okay, it doesn't matter, guys. It's the ballpark in there. The way I kind of did it, it was, as we had said it would be. Pretty fascinating stuff. Any way you want to do it. It's all there, guys. There's 1.31954. Okay. 1.31. Yeah, I said 1.32. Yeah. It's the way it is. It's fine. It's fine. The way we got it. It's okay. Getting the same answer there. So when you go with that, guys, let's actually kind of deal with it, if you don't mind. Let me... I got 479.90. Yeah, same answer. It's the same. It's the same play on the thing, guys. This is a good way to play it. I mean, this came out okay. The 1.3, 1.32, 1.3, 1954. On that. So there you go, guys. So we got here. BRMS. Ran out of room a little bit, guys, but you know where I'm coming from. Yeah, it comes out just fine, guys. Exactly, it came out. 479.90. You saw me make the argument earlier how we could proceed with that. I did it more with molar mass, and it came out a lot faster. Wasn't quite to the degree of specificity that they had, but man, it sure wasn't off by much. It was off by not even 5/10,000ths. You know, not even 1/2000th off of what it was. You know, so not too bad. That's it. I mean, there's other methodology, guys, but it came out roughly the same. I think that other methodology, it kind of came in right here, so I think that'll be fine. Look at it though; it's in the notes. I've got it posted on Canvas for you. Basically, following earlier derivations, we can come full circle back to numerous equations. Well, yeah, I mean, we got hit by that 3/2 thing all day long, right? 3/2 NKBT, 3/2 PV equals what? You know, the 3/2 NRT, 3/2 NKBT again. We've derived all that stuff again, guys. So we don't have to rederive it, but look at the earlier stuff. It's good to see. It's good to look at. Following earlier derivations, we can always come full circle back to numerous equations, and that's pretty good for us. All right, sounds good, guys. There's just one more chapter I wanted to do on thermodynamics, and I'll get to that. It'll be chapter 21 from the Katz book, and that'll be it. Thank you so much for your time, guys. Take care. Bye now.